4.7 is about first derivative interpretation. We're going to be looking at how a function relates to its derivative. So for our first examples, I'm giving you a differentiable function that also has a few other characteristics. We're told its derivative is negative on certain intervals. Second, the derivative is positive on other intervals. And third, the value of the derivative at 2 is the value of the derivative at negative 5, and both have a value of 0. We're going to use this information to answer some questions. All right, so before I start that, we're going to take the information we were given here. We're going to make our first derivative number line and fill in some information about f. Here's f prime's number line. We're told that at 2 and negative 5, the derivative has a value of 0. We're told that from negative infinity to negative 5 and 2 to infinity, our derivative is negative. And from negative 5 to 2, our derivative is positive. So I've interpreted my function and its derivative onto a number line. And we're going to use that to answer some of the following questions. So we're being asked about the derivative of g. We're told g is equal to f minus 7. So let's figure out what the derivative of g is equal to. So g prime would be equal to the derivative of the right side. So the derivative of f would be f prime minus the derivative of 7 would be 0. So the derivative of g is the derivative of f, which means the number line for f prime is the number line for g prime. So they have the same number line here. Negative 5 is a 0, 2 is a 0, and my signs are minus, plus, minus. So filling in the blanks with the following signs, how does the derivative of g here at negative 4 compare to 0? So negative 4 would fit in between the two values. And so what is the value of our derivative there? It's positive. So we want to say the derivative at negative 4 is greater than 0. Where does 3 fit in? 3 is bigger than 2. The value of the derivative at 3 is negative, so we would be less than 0. All right, so we're going to repeat this. But we're going to do that for some new functions. Number 2. All right, on number 2, g is defined as f of x minus 3. So we need to go ahead and find g prime now. So in this problem, the derivative of g on the left is equal to, starting with the outside function, the derivative of f and then chain rule times the derivative of x minus 3 would be 1. So this is what I get. So this is not quite f prime x. It's the derivative of f with a translation of 3 units to the right. So what I'm going to do is go back up here to this graph and shift everything 3 units to the right. So that would be shifting my x-axis values, that would be these values here, 3 units to the right. So if we do that, my zeros are no longer negative 5 and 2. So if I move negative 5 3 units to the right, it ends up at negative 2. And if I move 2 3 units to the right, we end up at 5. The signs, however, the values I get on top, these are my derivative values, my y values. So negative, positive, negative, zeros, these all stay the same. It's only the x values that have changed. The y values remain the same. So now g prime of 0, so where does 0 fit in here? The 0 would be between the two, where the derivative is positive, which means this value is greater than 0. Negative 2 is a 0 now, so my derivative is equal to 0. So let's do one more. This time g is defined as 2 minus f of x. So we're going to start with our derivative here. The derivative of g is equal to the derivative of 2, which is 0, minus the derivative of f, which is f prime of x. So this is almost similar to what we started with. But when I have a negative on the outside, instead of something affecting x on the inside, it's on the outside, which affects y, or the derivative of f. So what's happening here, instead of my x values changing, it's my y values that become opposite. So my number line now, my x values are the same as we started with for f, but it's the outputs, the y values on top, that have changed. The opposite of 0 is still 0, so that doesn't actually change. But my negatives become positive, and my positive becomes negative. So it's just the y values that change here. All right, so now we'll go ahead and line everything up. Negative 1 is between the two values, where the derivative of g is negative, so we have less than 0. And negative 6 would be to the left of negative 5. The derivative there is positive, so we'll fill in with a greater than 0. Okay. So those are some number line test interpretations. Now we're going to look at some problems that involve sketching our derivative based on the graph of the original function. For our last few examples, and there's only so much we can do here, so we're just looking for certain things to happen. Number 4, here is f, and we want to sketch its derivative on the same set of axes using the information we have here. So let's think about f. F appears to be maybe cubic, so if we say it's cubic, and positive since it is low to high, what would we know about our derivative? Our derivative would probably be positive leading term, x squared. So it should be like a parabola, high to high. We should look for certain values, though. My derivative is all about the slopes of the tangent lines. So all of them are positive here. All the slopes of the tangent lines are positive here. So my derivative should be positive on this interval. And for a graph to be positive, that means it should be above the x-axis. Then the slopes of the tangent lines become negative. So if my derivative changes from being positive to being negative, it must be because it went through a slope of 0 here. So right here, where the little maximum occurs for f, we should have a 0 for the derivative. Since my tangent line slope would be 0 here, that is where f prime is 0. So I'm looking for these values specifically. So is there another one? There should be. Right where there's a minimum, we would have another one. Okay, so that does help me with my parabola. It should be positive high to high. It has these two x-intercepts. Slopes of tangent lines are positive here, so my function should be above the x-axis. Slopes of the tangent lines are then negative, so in here, my derivative should be below the x-axis. And then again, slopes of the tangent lines all along this curve are positive, so my derivative would be once again above the x-axis. So here is f prime. So let's try that again with another function. Here's f. Okay. Not a nice smooth continuous function, some kind of a square root function. Its derivative is not going to be very nice. But here's what I know. At any end point, f is not differentiable, which means my derivative does not exist here. So my derivative should have an asymptote going here. Okay, again, f is not differentiable at endpoints. And so my derivative should have an asymptote here. Okay. Now when I have asymptotes, anytime I have a vertical asymptote, I should have a piece of the function on each side. Well, that's not going to happen this time, because if f only exists to the right of the vertical asymptote, then f prime only exists on the right side of the vertical asymptote. So I'm only going to have f prime exist over here somewhere. And the last thing I want to do is think about those slopes of my tangent lines. So notice there's nowhere where I would reach a max or a min, so no zeros for this one, so never going to touch the x-axis. Let's write that down. No max or min means no 0 for f prime. What do you notice about the slopes of every tangent line along this curve? Is that they're all positive. So that means my derivative is always positive. For a graph to be positive means it lies above the x-axis. So I already knew it wasn't going to cross the x-axis, and it had to be over here somewhere, either on top or underneath the x-axis. So it has to be above it. Again, because my tangent line slopes are all positive, my derivative must also be positive. So here is f prime. Let's do one more. Starting with the graph of f, which seems to be parabolic or possibly x squared. And then you'll notice low to low means it has a negative leading term. We won't worry about what follows, whatever the rest of it is. It's really just the highest power case that we care about. Then we notice there is somewhere where the function has a maximum. So that means there is somewhere where my derivative should equal 0. That would be at this point here at the maximum. So right down to our number line here. is where my derivative should cross the x-axis. What else do I know about f prime? Well, if it's the derivative of f, its highest power should just be x to the first. Negative x to the first. So this would just be a line with a negative slope. So do I know how steep the slope should be? No. You can make it really steep, or you can make it very shallow, or somewhere in between. It doesn't matter because we don't know. It's important that we show a negative slope and that we have a 0 where there should be a 0. Okay.